Hello, in this video we're going to be talking about kind of a tricky but really important conceptual topic that has to do with the composition of a chemical compound. So I'm titling this video, How Many Moles Are in a Mole? And that kind of sounds like a trick question, but I don't really mean for it to be. What we're actually talking about is the concept of how many oxygen atoms are in a certain number of carbon dioxide molecules, or how many moles of oxygen are in a certain number of moles of carbon dioxide. So let's hop over to a new page and let's kind of start thinking about this conceptually. We'll actually use CO2 as the example there. So CO2 is going to be the molecule that we use in our example. It's kind of nice and simple and will keep the numbers pretty friendly for us. So we have CO2. Let's draw one here. So there's my little carbon dioxide. We got carbon in the middle. That's the little white circle that I've drawn. Then we got two oxygens on either side. So those are the two little red circles that I've drawn there. So if we take a look at carbon dioxide, if I have one CO2 molecule, so if I have one of these whole things, I'm going to have two oxygen atoms as a part of that whole molecule. So in other words there, my ratio of CO2 to O, or oxygen, is 1 to 2, right? So again, the idea here is one of these molecules provides me with two oxygen atoms. Okay, so what if we had two carbon dioxide molecules? So there are my two carbon dioxide molecules, and we can see that if we have two CO2s, let's count how many oxygens we have. 1, 2, 3, 4. So two carbon dioxides gives us 4 oxygens. Now you might notice that that ratio, 2 to 4, would reduce to 1 to 2. Okay, so that's pretty interesting. So let's keep going. What if I had 3 carbon dioxides? So there are my 3 CO2s. And again, let's count how many oxygens are present here. So I've got 1, 2, 3, 4, 5, 6. So 3 carbon dioxides, or 3 CO2, would give me 6 oxygens. And again, you might notice this ratio, 3 to 6, reduces to 1 to 2. All right, let's keep going. What if I had 18 CO2s, 18 carbon dioxides? All right, there they are. And you could pause the video to count these if you want to, but they're there, 18 carbon dioxides. So how many oxygen atoms would be there? Well, we could count these out, or we can start thinking about this ratio that's represented here from the chemical formula, right? A 1 to 2 ratio. In other words, we always have twice the number of oxygen atoms as we do carbon dioxide molecules. And so 18 times 2 is 36. 36 oxygens. And again, we could go through and we could count all the oxygens in our little molecule diagrams over here on the left, and there would be 36 there. Now we're going to extend the same line of thinking to a more realistic number of molecules. Very rarely would we talk about 36 carbon dioxide molecules or 18 carbon dioxide molecules, right? Most of the time we're talking about a pretty large number of these things. So what if we had something like 1.2 times 10 to the 22 carbon dioxide molecules? How many oxygen atoms would be present there? Well, just like we did previously, we could draw all these out and count them. However, I don't know that I want to draw out 10 to the 22nd carbon dioxide molecules. So instead, I'm just going to use the ratio that we have here outlined in pink, the idea that there are always twice the number of oxygen atoms as CO2s. And so 1.2 times 10 to the 22 gives me, times 2, gives me 2.4 times 10 to the 22. And you could use the calculator for help with that if you wanted to. So again, that ratio is still upheld. All right, let's go even bigger. What if we had 6.022 times 10 to the 23rd CO2s? So again, we're going to extend the line of thinking that we have here, that this is always a 1-to-2 ratio. And so to figure out how many oxygen atoms we'd have, we're just going to double this number. So 6.022 times 10 to the 23rd times 2. Again, we could go to the calculator and we could get a little bit of help with that. But that comes out to be 1.2 times 10 to the 24th. And I rounded a little bit there. But the idea is that we have doubled that number. Now at this point, our numbers are getting pretty big here, right? This is, 10 to the 23rd, 10 to the 24th. Those are pretty big numbers. And 6.022 times 10 to the 23rd, hopefully that is a familiar number to you. That is Avogadro's number. That's the number of things, in this case molecules in 1 mole. And so we could do a little bit of a unit change here. We can go from talking about molecules of CO2 to moles of CO2. So in other words, if I took each of these numbers here that I've outlined in blue, and I divided them by 6.022 times 10 to the 23rd, to change my units from molecules of CO2 to moles of CO2, or atoms of oxygen to moles of oxygen, I would get a 1-to-2 ratio in terms of moles. And again, note that this ratio here, 1-to-2, is what we outlined at the very beginning based on the chemical formula. This is no coincidence. This is law of definite proportions, which might sound familiar. It was one of the 3 fundamental laws we talked about back in first semester when we were getting informed about atomic theory and atomic structure. Okay, let's hop over and let's look at the type of problem that we'll see where we have to apply this line of thinking. Okay, in this example, we're asked how many moles of oxygen are in 2 moles of Cl2O7. Now, there are a couple of ways you could solve this problem. I'm going to show you the simplest and most direct way here. If you want to see the longer way to solve it, you'll find that in the notes linked in the description of the video. But for this video here, we're going to keep things kind of simple and straightforward. So I can solve this problem by setting up 2 equivalent fractions. In my equivalent fraction on the left, I'm going to write the ratio of Cl2O7, which is the compound that we're working with here, to oxygen, which is what I'm asked for in the question, based on the chemical formula. So I'm just going to get those numbers from the chemical formula there. So 1 mole of Cl2O7, right? If I have 1 mole of that compound, is going to contain 7 moles of oxygen. And again, I'm getting that 7 from the chemical equation there, right? Because it's O7, Cl2O7. On my equivalent fraction on the right, I'm going to put in the conditions that I'm given for the question. So in the question here, I'm told that I have 2 moles of Cl2O7. And we're going to solve for moles of oxygen. So we can just say like X moles of oxygen. All right, now we get to do everyone's favorite thing. We get to cross multiply. So we're going to do 7 times 2.0. And that is equal to 1 times X, or X. So in other words, X is equal to 14 moles of oxygen. And that's our answer. So we've taken this ratio here in my equivalent fraction here on the left. So we've taken this ratio from the chemical formula, right? And we know that ratio is always going to be true. It's always going to be true. That's the law of definite proportions. So then we just set it equal to the conditions we're given in the problem, and we solve for our unknown. Again, you can do this problem in a more lengthy calculation using percent composition by mass. That is going to require some unit changes, require you to use molar masses, that sort of thing. If you want to see that calculation shown, again, you can find that at the end of the notes that are linked in the description of the video. I kind of write that out and show that. Okay, let's look at another example that is a little bit more involved. There's going to be a few more steps here, but you'll see that in the middle of this calculation that we're going to do is what we've been talking about in the video, using that mole ratio. So I want to know how many carbon atoms are in a sample of sodium hydrogen carbonate, or NaHCO3, that has a mass of 12.4 grams. Okay, so you can see this is a little bit different than the example we just looked at, because my starting units here aren't in moles, they're actually in grams. Again, there are a couple of different ways that you can do this problem. I'm going to do it using the equivalent fractions and the mole ratio from the chemical formula, because conceptually I think that's a really important idea to be able to latch onto. Okay, so the first thing that we can do here is we're just going to take whatever value that we're given in the problem. So in this case, it's this 12.4 grams of NaHCO3, or sodium hydrogen carbonate, and we want to turn that into moles. And we're at the point of the year now, if you're watching this video, you're at the point of the year now where that idea is going to be a really good and correct first step for a vast majority of the problems we do this semester. Just convert to moles first. Moles are much easier to work with, and a lot of what we do this semester, we have to be in moles anyway. Okay, so that's my first step, is to convert from grams to moles. All right, so the way we convert from grams to moles is we divide by the molar mass of that compound. Now, I've not shown that addition of the molar mass here, but I did calculate it, and it came out to be about 84.014. So in my calculator, I'm going to do 12.4 divided by 84.014. And the calculator shows me 0.1475944. Being really careful not to round too much right now. Right, I don't want to round for sig figs quite yet because we're still in the middle of our calculation. Okay, so now that we're in terms of moles of NaHCO3, we can figure out how many moles of carbon are going to be in this sample. And we're going to do that using the equivalent fraction setup that we've been talking about during this video. So here are my equivalent fractions. Again, the way I tend to set these up, the one on the left, I am setting up based on the chemical formula of the compound. So one NaHCO3 actually only has one carbon in it, so we're doing a 1-to-1 ratio there. And then on the right side of my equivalent fractions here, I've got the number that we calculated at the end of step 1, so 0.1475944 moles of NaHCO3, and then we're going to solve for moles of carbon. Now again, this is a 1-to-1 ratio, so that makes our math pretty easy. So X in this case, or moles of carbon, is going to be 0.1475944. All right, we're almost there. We do have one more step. So right now our units are in moles of carbon, And we want our units to be in terms of atoms of carbon. So we got to do a little bit of a unit conversion here at the end. So we're going to convert to atoms. I'm going to try to squeeze this in here at the bottom. So to do that, we're going to multiply our number of moles that we have calculated. Moles of carbon. And we know that there are 6.022 times 10 to the 23rd atoms in 1 mole. So we're going to use Avogadro's number there as our conversion factor. Okay, so we throw that in the calculator and then round our answer to 3 sig figs, and we get 8.89 times 10 to the 22nd carbon atoms. And that is our final answer. So same general idea that we've been talking about, but notice that we got to do a little bit of unit conversions there to moles and then from moles in order to use this equivalent fraction method that we've shown in number 2. All right, we're gonna hop over to another board and I'm gonna work through this same example, the same calculation, but I'm gonna show you a little bit more of a streamlined way to set it up. And I think it'll look kind of familiar once you kind of see it all laid out. Okay, so here we are, same example that we just worked through, but I want to show you, again, a little bit more of a streamlined way to set this up. And I'm going to borrow sort of a lot of our setup here from dimensional analysis, and when we were talking about, these kind of long dimensional analysis problems and unit conversions. I want to note that it's not required that you show the setup this way, but this might help you kind of organize your work and see it laid out in a little bit more of a kind of a direct and linear way. Okay, so here's our setup. And I want to talk through what I have written here because there's a lot of numbers that just appeared out of nowhere. So if you remember on the previous slide, we sort of broke this up into 3 distinct steps. So in step 1, we converted from grams of NaHCO3 to moles of NaHCO3. In step 2, we converted from moles of NaHCO3 to moles of carbon. And then in step 3, we converted from moles of carbon to atoms of carbon. Okay, we have done the same thing here. This first unit conversion here, 1 mole of NaHCO3 is 84.014 grams. That's the molar mass of NaHCO3, and that gets us from grams to moles. And you can see the way we've set this up, very dimensional analysis like, where our units are going to cancel out, units of grams are going to cancel out, and now we're in moles of NaHCO3. The second conversion factor here, 1 mole of carbon over 1 mole of NaHCO3, comes from the chemical formula, right? We showed this as equivalent fractions in our last couple of examples. We could also write this sort of as a conversion factor like this. So again, notice we put moles of NaHCO3 on the bottom so that we can cancel those out. And after the second step, we're in terms of moles of carbon. And then our last conversion factor here, 6.022 times 10 to the 23rd atoms over 1 mole of carbon, is that Avogadro's number conversion. That gets us from moles of carbon to atoms of carbon. And again, we've set that up so that our moles of carbon or moles of C cancels out. So it's the same calculation, just sort of written out in a very similar format or a very familiar format. If we popped it all in the calculator, we would end up with the same answer when we rounded for our sig figs, 8.89 times 10 to the 22 carbon atoms, or atoms of carbon. And that is how we calculate how many moles are in a mole. I hope that was helpful. Thanks for watching.